Hello, and welcome to this session of Lean Six Sigma Green Belt Control Phase. This is the last phase of DMAIC, and we are into the control phase. As usual, we know that this session is driven using Minitab. In this particular session, we will look into control charts using Minitab. We will look into the basic concepts, theoretical concepts, and then we are going to discuss the case studies on which control chart to use given a particular situation. Why did I put this image here? We are looking, probably it is a fly, right? I wish to say you that Drosophila fly eggs are measured in the canned orange juice, citrus juices. Is that true? Oh yes. How do they monitor that? Using something called as control charts. We will get into the depth of the control chart. We will discuss about various concepts there. Just to give you a brief about this, let me explain this control chart which is present here. Upper specification limit and lower specification limit are provided by the customer, end user. And these specification limits will not change. They would remain the same. And your control limits, upper control limit and lower control limit, these limits are calculated based on the data points which get generated. And these black dots, these are your data points, right? And here we have the mean. Let us understand this using cricket ball example, right? And later on you can relate to how insect fragments are measured in citrus juices. How is the maximum content of your Drosophila or fly eggs within citrus juices, canned citrus juices, is measured. All right. Let us understand this example using cricket. Cricket is a game which is played and it's extremely popular in India. And it's popular across the globe as well, right? So cricket, if you all are not aware, assume that it's played with a ball, right? Which is called as ICC cricket ball, right? And ICC stands for International Cricket Council. This International Cricket Council provides you the limits, saying that, hey, no cricket ball circumference should be greater than 229 mm. No cricket ball circumference should be lower than 224 millimeters, right? That's the unit there. Why do they provide these kind of limits? Because if they do not provide so, manufacturers might manufacture a cricket ball whose circumference might be 250 mm. If it is 250 mm, you end up playing cricket not with a cricket ball. You end up playing cricket probably with a volleyball, right? A ball which is bigger in size in comparison to your cricket ball. Why do we have these lower specification limits here? Because if International Cricket Council does not give these limits to you, you might manufacture a ball which is the size of a table tennis ball and say, hey, here is a cricket ball, go play cricket with that, right? So if you are not going to provide these kind of specification limits to the manufacturers of the cricket ball, there is no guideline based on which they can manufacture the cricket balls. Hence, we have these kind of limits set. There might be control charts with only your upper specification limit, as in case of these fly eggs, right? There should not be more than 5 Drosophila and other fly eggs per 250 ml of canned orange juice. 250 ml of canned orange juice. That is measured according to Food and Drug Administration US, FDA. Alright? So that is upper specification limit which is set. Lower specification limit would obviously be 0. You can have such situations also. Right? Or in 250 ml of canned citrus juice, there should not be more than 1 megot. Megot is an insect, right? A weird looking insect. Not more than 1. Right? These kind of limits are set to ensure that you, oh my bad, once again. So we can just have the upper specification limit, as in the case of your Drosophila fly eggs, or megot, which is measured in 250 ml of citrus canned juice. Or on the other side, you might have only the lower specification limit without the upper specification limit, as in the case of productivity. If you were to measure productivity, right, do I have an upper limit on that? I most often than not do not like to have an upper limit on my productivity. I do not want to keep a tab on that. Higher the productivity, better it is for me, probably, right? Probably. So in some cases, you have only lower specification limits. In some cases, you can have only upper specification limits. And in some cases, or most often than not, you'll have both upper specification limit and the lower specification limit. Let us take another example. Say I want to monitor my effort variance, right? And say my organization gives me this goal, which says upper specification limit is 10% and lower specification limit is minus 10%. What does that mean? This means that for each task, right, say task 1, I have the planned effort. Planned effort could be, say for task 1, say it is 100 hours. For task 2, say it is 120 hours, things like that. This plus or minus 10% upper and lower specification limits, right, say that this task should not take more than 110 hours, right? Or it should not take less than 90 hours. How did we get this 110? It is plus 10%. 100 plus 10% of 100 would take the count to 110. So you start monitoring against this upper specification limit, right, for task 1. How did we get this 90 here? It is 100 hours minus 10%, which would be, or minus 10% of 100, which would be 90. I need to complete this task 1 within these limits. Though the planned effort is 100 hours, I'm not going to be alarmed, right? I will not be confused. I will not take any action if the actual effort turns out to be any number between these limits. If it is greater than 110, say you were supposed to complete this task 1 in 100 hours, however, you have taken 115 hours. That is an alarm for me. I've exceeded the upper specification limit. I would go back and analyze what went wrong. Why did I spend so much of additional effort as opposed to the planned effort of 100 hours? And then I try to identify the root cause using fishbone and or a 5 why analysis and try to address the root cause. This scenario is okay. If I overspend, I'm going to do that. However, think about the lower specification limit, which is 90 hours here. If I complete a task which was planned for 100 hours, if I complete this task in 80 hours, effectively speaking, I've saved 20 hours, right? I should have completed the task in 100 hours. That was a planned effort. However, I've taken only 80 hours. Why do I need to even monitor that? Why should even I be concerned about that? Why should I be alarmed about this? I should be alarmed because probably I might have compromised on the testing, or my estimations might be wrong. My planned effort might be a wrong estimation. Or maybe I've missed out on a particular feature or functionality. Anything is possible, right? So you need to analyze it to identify whether this is really a bad situation, or is it a good situation wherein you have come up with some reusable component, you have done some process improvement, which has ensured that your 100 hours of planned task was completed in 80 hours. Don't you want to document the best practice? You want to do that, right? Because we want to replicate the best practices. That is the reason why we have upper specification limit and lower specification limit in most cases. And remember, your specification limits are provided by the customer. That is fine, but what are these numbers? Control limits. Control limits are statistically calculated based on the data points that you enter. These are the data points that you enter. Let us go back to the cricket ball example now and understand the control limits. We know that the upper specification limit for manufacturing the cricket ball is 229 mm and the lower specification limit is 224 mm, right? These are the specification limits given to me by my customer. Say I've manufactured the first cricket ball and its circumference, say, is 226 mm. You'll just jot it down on the control chart. If this is 224, if this line is 224, and if this line is 229, then 226 would fall somewhere here. Say the next cricket ball that you have manufactured, its circumference is 227.5 millimeters, right? Then you plot another point on this control chart. Say the next cricket ball that you have manufactured, say the circumference of that was 226.5 You plot the third data point. So on and so forth, as in how you manufacture the ICC cricket ball, as in how you get the circumference of that, you jot it down on the control chart and record it. The moment you have n number of data points, these control limits are automatically statistically calculated, right? The moment you plot another data point here, right? Again, your control limits might tend to change because they are statistically calculated. They are dynamic in nature. All right. So this is how it gets calculated. Now we'll do a deep dive also. I've just given you a high level overview of what control charts are because, you know, we would be spending some time analyzing that, and we'll also understand some of the terminologies within this. Okay, going back to our equation, y is equal to f of x, right? In the define phase, we have defined what is the output which we want to achieve. In the measure phase, we have measured the current status of your output, which you want to achieve. And then in analyze phase, we have identified all the potential x's. And then we have shortlisted the critical inputs, critical x's, which would impact your output. And then we have improved those inputs, critical inputs. Now our job is to monitor and control the improvements which we have brought in. For that, we are going to get into the control phase, wherein we monitor and control both our inputs and also our outputs. You can monitor both of those, control both of those. All right, now let us get into the agenda of this control phase. Here is the course objective. We are going to first look into the three-step control phase. And the 3 steps are as follows. Control the critical inputs, solution and benefits documentation, hand over the improved process to the project owner, and move on. We are going to look into a lot of things such as control plan checklist. We will look into mistake proofing, which is also called as pokayoke. We'll look into what is the difference between defects and errors. We'll look into mistake proofing techniques and benefits, visual standards and visual controls, inspection and audits. Then we'll do 5 case studies around statistical process control, that is control charts. And then as usual, we're going to summarize and we'll move ahead. Here are the 3 steps of control phase. We need to first control the critical inputs. Also, we use control phase to control your output, right? We also do that. Solution and benefits documentation is the next step. We document the solution which we have provided, the benefits that the solution has given to you. We document all that. And then we hand over the improvement or the improved process to the project owner for him to, continue with the analysis. All right, let us now discuss how to control the critical inputs. First things first, we need to come up with the overall strategy for improving the process performance over time, right? We need to come up with a strategy for maintaining the improved process. You have improved a process does not mean you're going to leave it aside. Remember, we have discussed in the measure phase that the improvements that you bring in now, no matter even if it is Six Sigma process, if it is left unattended or if you do not do any continuous optimization or improvement on that, your sigma level is tend to drip by 1.5 sigma, right? Say you have a process, after improvement it is at 6 sigma, assume. If you do not do any improvements on that, it's going to drip down, and how much will it get degraded by? 1.5 sigma, and this is statistically proven, right? Hence, we need to always be on our toes. We need to improve the improved process. We need to maintain the improvement and also try to improve it further. That is our objective. What are the objectives of the control system in that case? We want to identify the specific actions and tools required for sustaining the process improvements or gains. That is the first thing. What should I do? What actions am I supposed to take? What tools am I supposed to use for sustaining the process improvements, which we have brought in with such a great difficulty, right? We have literally spent a lot of effort in analyzing the data, crunching the data, bringing business insights from the data, right? If you have spent so much of effort, it is worth spending some time in coming up with the specific actions and tools which are required to sustain the improvements or gains which we have brought in. We also want to ensure that a process stays in control. I've implemented a solution doesn't mean I'm going to take a back seat, does not mean I'll be laid back. Instead, I'll ensure that this improved process stays within the control always. That is extremely important. If there is any out of control situation, we should be able to quickly detect that and take an appropriate action, right? We should be able to identify what is the special thing which has happened because of which a process was out of control. Special causes. Anything which falls outside your control limits or specification limits for that case would be your special case, because you can assign a special cause to that on why it went out of control. All right, Here is a typical control plan, and these are the various components of a control plan. You would have a data collection plan. We need to have mistake proofing system, which we are going to discuss in detail. We need to address the risks, not just mitigate the risk, but we also have to look into various other mechanisms of coming up with the risk response strategies for both your positive and negative risks, by the way. Right? You know that risk is any uncertain event which might occur in the future, which might have negative or positive impact on that. If mistake proofing is not possible, then we'll come up with statistical process control as part of your control chart. That is the next best solution. The first best solution is mistake proofing. Do not let people make mistakes even if they want to. Right. The next known solution is your statistical process control using your control charts. If that is also not possible, probably you'll resort to mechanism of conducting the audits or inspection. By the way, that is the least preferred. Process ownership, who is supposed to own the process? Process owner, right? What is the response or reaction plan if something goes wrong? And then we also document the process. So these are the various components of your control plan. Now let us understand a few more things about this control plan. Here we go. Control plan is not a replacement for your detailed instructions. If you have standard operating procedures for your various departments, control plan is not a replacement for that, right? It's just a supplement. It is documented description of systems which are used in minimizing the process and service variation. It documents all the systems, it documents your processes, right? To ensure that the variation in the process or the service which you're providing is to the bare minimum. It describes the actions that are required at each phase of the process, right? It describes the actions for each of your inputs, each of your outputs, right? And periodic requirements to assure that all process outputs will be in the state of control. All cricket balls that are manufacturing should meet the specification limits. The circumference of all cricket balls that are manufactured should be within 229 to 224 mm. That is all about that. Control plan is a living document. What do you mean by a living document? Is it going to walk now? No. Living document means this is not a static document which is written once and does not get updated anytime, right? Control plan gets updated throughout the project of Six Sigma. Even after that, if you have any changes, if you have any good suggestions, good improvements which you bring in, even after the implementation of Six Sigma, you're free to do that. It contains few of the things such as what process is being controlled, what measures are being monitored, right? Are there any trigger points for each measure? If yes, what are those? What actions are you going to take when there is a trigger point? And last but not the least, who is responsible for taking action? Who would take the action? That is most important part here. Next thing is your control plan checklist. You need to have a checklist in place and ensure that your control plan is complete. How do you do that, and what are the key components of your control plan here? The first thing is process maps, right? Because now the process has changed. So the changed process map, the various process steps, information flow, and the important variables should be part of your checklist. Key service variables, key variables which you have identified by giving more importance to your customer, by giving importance to the desired target value and the specification range. You need to document that, right? That's the second checkpoint. We all have discussed already about capability indices, right? CP, CPK, right? Long-term, short-term, Z values. We have discussed about all these things. These trend charts are required to track the variation reduction progress. You document the critical input variables, right, which are identified with the relevant targets against each of those, right? Statistically determined control limits. When you plot the control chart, you would get the statistically calculated control limits. And what are the control strategies that you have defined there? You also come up with the reaction plan. If process is out of specification, out of control, what would you do? How would you react? Are you going to do an analysis on that to identify the root cause? Oh yes, you'll do that, right? So you document that. It's as simple as that. Have a checklist in place. We have already done the measurement system analysis even before we started the analyze phase, right? As part of our measure phase. However, now the process has changed. You have brought in the improvements. Post improvements, is your measurement system still capable of measuring accurately? You do that. You need to have a checklist there. How do you do sampling? Are you going to use a simple random sampling or will you go with strategic sampling, right? How are you going to do the inspection, right? Are you going to inspect the entire population? Maybe if very few things are manufactured, you inspect the entire population, maybe, right? But if there are a lot of things which are getting manufactured, for example, if you're manufacturing 1,000 shirts per day, inspecting all the 1,000 shirts does not make sense. It's not worthy of investing so much effort there. So what do you want to inspect in that case? Probably just 10% of the total 1,000 shirts which are manufactured. You need to have a checkpoint against that. And testing plans, right? How are you going to test everything? Also, how often are you going to do the inspection, on a daily basis? Or would you do the inspection, sampling, or testing on a weekly basis? Right? Where will you do that? At the customer site or at the manufacturing site? Or in your godown, in your logistics, in your inventory store? Where are you going to do that? And to whom are the results going to be reported? There should be someone, right? Some key stakeholder to whom you send the reports to. You need to have that information also handy here. Standard operating procedures are going to identify the actions, responsibilities, roles and responsibilities primarily. Are you going to do any maintenance on your current machines or things like that? If yes, what are the maintenance schedules? And service segregation requirements. How are you going to segregate the service from your different operations, different projects, and things like that? Training materials are extremely important, which are going to describe the aspects of process operation and responsibilities, right? Who is going to train? How are you going to train? Right? What is the process improvement that you have brought in? You need to train the people also, right, on the changed process. That is extremely imperative. Process improvement efforts, which are fully documented and available for reference. That is also another important thing. And then you have your control plan, which is reviewed and updated on a quarterly basis. Or in few places, they update it on a monthly basis. In few organizations, they update it on half-yearly basis or yearly basis, depending on the amount of change that is brought into the process. Quarterly seems to be an apt, and a safer bet, right? And it resides in the operating area. You do not put your control plan somewhere in your drawer, somewhere in your cabinet. It should be available for everyone for reference. Hence, you put it in the operating area. That is all about your control plan. And needless to say, this is something which, naive Six Sigma consultants would miss out upon. You need to document that. A good Six Sigma consultant would do this. Then we have mistake proofing. Here you have someone, who is doing skydiving. Just think about that. Midway, when he wants to open the parachute, it doesn't open. Such a scary situation, isn't that? It's extremely scary situation. Such a scary sight, is it? Right? If you're doing skydiving and midway your parachute doesn't open up, isn't that extremely scary situation, right? People have ensured to the core that those kind of mistakes do not happen. Once it drops to a particular altitude, it automatically triggers on the parachute. That is mistake proofing. Look at that. This person has a device on the hand, on the wrist, which says that, hey, you're dropping to a situation or to a height altitude where automatically the parachute would open up, even if you do not want to do so. That is mistake proofing. I'll not let you commit suicide. Mistake proofing, or pokayoke, it's famously called as pokayoke also, is a technique for eliminating errors. I'm going to ensure, or I'm going to make it impossible for you to make mistakes even if you want to. That is mistake proofing. Look at this simple example here. Switchboard has a square opening here, and the plug here has round slots. These round things would not get into this. You have done a blunder. Instead, if I come up with this kind of a switchboard, then easily you can put in that plug, right? That is called as getting rid of mistake proofing. Or sorry, mistake proofing, right? Even if you want to insert this into this square switchboard, you cannot do that, right? You can put that only into this. That's mistake proof. I will not let you make mistakes even if you wish to. Even before we discuss more about the mistake proofing concepts and things like that, let us understand what is defect and what is an error. Are they both the same? Oh no, they are not the same. Defects are the results of the error which you make, and the error is going to cause defects, right? Cause causes the effect, error causes defect product, mistake causes incorrect product or damaged product or incomplete product. How do I get rid of that? Let me ask you the simple question here. You all are aware of USB slots, right? Did you ever undergo any training on USB? Have you done that? Universal Serial Bus, right? USB. Have you ever undergone this training? Ever in your life? No, right? No. Why didn't you undergo? Because there is no such training. Can I take this USB device and plug it into any other slot other than my USB slot? Can I do that? I cannot do that. That is mistake proofing. I will not let you make mistake even if you want to. That is the number one control strategy that we need to be banking upon. Though it's costly, it's going to stay there for a longer period. The effort that you spend otherwise on the inspection, audits, controlling that is gotten rid of. Here is a traditional view, and here is a Six Sigma view on how to minimize the defects. So the traditional view says that people are only humans. They tend to make mistakes, and inspection is necessary. That is what your traditional view about minimizing the defects is, right? Well, what does Six Sigma say on the contrary? Many human errors can be eliminated and remaining can be reduced. The need for inspection can be reduced or eliminated altogether. That is a Six Sigma view of how to minimize the defects. Here is the mistake proofing. Mistake proofing is the best control mechanism, is the best known technique to control the improvements which you have brought about. There are three different categories within that. The first technique is shutdown, right? In prediction or prevention, when a mistake is about to be made, you come to know that, hey, there is a mistake which is about to happen. And the entire world is moving towards that, building prediction models, data analytics, and all that. Detection is when a mistake or defect has been made, you come to know that, hey, there is a mistake which is done and it's going to automatically shut down. If your car is overheated, it's not going to start. We're going to look into the examples for each of these techniques, right? Control is another technique of mistake proofing. Errors are impossible to be made in control technique of mistake proofing. In detection, defective items cannot move on to the next step. We'll discuss that. We'll discuss all these things with examples, by the way. Warning is another technique of mistake proofing. With respect to your prediction or prevention, something is about to go wrong and there is a warning message which you receive. In detection, immediately when something goes wrong, you get to hear a warning message. When there's a fire, there would be a fire alarm. Things like that, right? Look at this. Well, I like this example, right? So this is a washing machine, which is also used to churn lassi, right? So look at how they're trying to abuse this product, washing machine, to churn lassi. It's the greatest challenge for most of the product-based companies to ensure that the product is not abused. Here it's getting abused, isn't that? People churn lassi in washing machine and start complaining that my machine has gone for a toss. We need to get it repaired. Look at the amount of warranty cost or repair cost if people come to you saying that the washing machine isn't working as expected, right? They might have done something weird like this. Next time when you drink lassi at anyone's place, check with them on when did they wash the clothes, right? Okay. Here is another example. If you put a screwdriver on top of the screw and try to fix that, there are high chances that the screwdriver might slip out. However, if I provide a screw like this, there is no chance that your screwdriver is going to slip either side. That is mistake proofing. All right, here are the examples of shutdown. For prediction or prevention, right? When a mistake is about to be made, it's going to shut down itself. Think about the good old days when we had these cameras, right? If there was no enough light, you cannot even take the snap. You cannot even take a photograph. That is shutdown all about. Detection. When a mistake or defect has been made, for example, when your laundry dryers reaches a particular temperature, it is going to shut down itself automatically, right? That is detection example. Here I'm not even letting you take a photograph and then repent, saying that it did not come up well, right? I'm not giving you an option to take a photograph if there is no sufficient light there. And then you have detection here. Then you have prediction, prevention for control phase. Not sure whether you have given a close attention in the gas stations, right? The nozzle for the leaded gasoline versus the unleaded gasoline, right, is different. The nozzle is different for both of these. So even by accident, I cannot, you know, put unleaded gasoline into the leaded gasoline, or I cannot put petrol into diesel vehicles or diesel into petrol vehicles. Even by accident, I cannot do that. That is called as prevention. I'm preventing you from doing mistakes. Errors are impossible to be made here. Let us look into detection part of that. Defective items cannot move on to the next step. If you go through this Apple conveyor belt, right, this is what happens. If you wish to segregate the good ones from the big ones, the biggest apples and the smallest apples based on size, it's going to divert. So the bigger apples will get diverted to a different belt altogether. Say there are a bunch of apples which are going through your conveyor belt here. Based on the size, you divert that, right? Based on the size, you divert that. So probably the bigger apples take this route and the smaller ones take this route. There would be something here which is going to check the size and then divert the apples there. That is detection basically in the control, right? So let us move on and understand the next thing also. Let us move on to the next slide there. The third thing is warning. This is the third part of your mistake proofing. If you do not wear a seat belt, it is going to give you an alert. It says, hello, you have not wore your seat belt. You have not put on your seat belt. That is prediction or prevention. Even before something goes wrong, the system is warning you. It's giving you a message. And the detection is your smoke detector. If there is a fire in a house or in any place, location, based on the smoke, you'll hear an alarm, fire alarm, and then you rush out, right? That is detection basically for you. What are the benefits of mistake proofing? There is no formal training required. Remember, USB device. Do you need any training to plug in your USB device into your systems? No. No formal training is required. Inspection is not required. So the effort that you spend on inspecting and performing your audits, things like that, got eliminated, right? The effort saved can be spent towards your futuristic tasks. That's another good news. You come up with a defect-free product because I'm not even letting you make a defect. I'm not letting you come up with a defect, right? I'm not giving you that opportunity. If there are no defects, obviously there wouldn't be any rework. These are a few of the good things, right? One more thing here. There is a person by name Tal Goldsworthy, right? He has used mistake proofing very effectively. Let me show you that. Right, let me show you that. Tal Goldsworthy, and he's a person who got his heart operated. Tal Goldsworthy, right? And he speaks a lot about that. He's a boiler engineer. He just knows piping and plumbing. And he underwent an interesting surgery, heart surgery, right? And he has mistake proof that. Here is an article from BBC. He's an engineer who fixed his own heart. Sounds cool, isn't that? He lived with a life-threatening issue that was less than easy to fix. There, he has come up with a simple solution. And he has implemented the mistake proofing concept. So mistake proofing is used to even save the lives of the humans. That is the power of mistake proofing. You can go through that when you find free time there. Next, we move on to the next best solution in control phase to control the improvement that you have brought in, and that is called as visual standards. Here is a visual sign, right? This says that, hey, this is a public calling office. You can make public calls there. This is a symbol or a visual of your suggestion box. Drop in your suggestions here. This is as a visual representation of the control chart. Visual communication. I try to communicate using signs. The next thing is visuals, which are used to control the mistakes. Hey, do not smoke. Do not switch on the lights, right? And these are the traffic lights. These are the visual controls which are used to control the mistakes that you might accidentally tend to make, right? Your airports do a lot of experiments around this before they open to the general public, right? They do a lot of experiments around that. They leave few people, or they open it only for a few of the public. The airports would be open for probably celebrities and things like that. And they monitor using cameras. They check how much time is a person spending in reaching his destination or his desired gate number to board a flight, or how much time is it taking from the entry to the aero bridge, right? If it's taking a lot of time, wandering about, that means your signages or visual communication or visual boards are not clear. Probably one person wants to go to a washroom and he spends 10 minutes identifying, roaming here and there, checking at the boards, and finally he finds a washroom. Hopefully by then nothing weird happens, right? So that means the visual boards are not clear, the visual controls are not clear, the visual standards are not clear, not well established. So a lot of your airports and public places, shopping malls, even before it's open to the general public, they do these kind of testings there, right? Hey, here is one such visual control, right? Go straight for your baggage, or to get a taxi, or to board a flight, right? And these are the various gates. These are your visual controls primarily. Visual control is any communication device which is used in the work environment that tells us at a glance how work should be done. How should you do the work? Probably it's there at the work environment which is going to guide you on how the work should be done. Always it's good to have visual control. Look at that. Before a visual control, this image looks good, but then what does that mean? Here, it's clear. This is a fuel gas. There is another, symbol attached here. If you have these kind of visual controls, it's going to make your life much easy, right? These are production displays, your traffic signals. All these are examples of your visual control. It generally applies to information which is critical to the flow of your work activities, such as your equipment. Safety warnings, extremely important, right? It should be clearly displayed if there is any safety related issue there. Actions, procedures, all those should be there. Standardization can be implemented in any situation in such a way that all standards are identified by visual controls. You standardize your work using visual controls, right? Once you have visual controls, you need not even worry about, directing people on what to be done, what not to be done. They take care of that. If you want to plug in your television set with your DVD set, right? You normally see these kind of slots. There would be a yellow slot. There would be probably blue slot there. And there might be another red slot for television, right? And you might have Similar these kind of slots for your uh, music system, and you just plug in red into red, blue into blue, and yellow into yellow. That is an example of your visual control on how to standardize things. All right, now, if that is not possible, then you resort to this technique of inspection or audit. Should this be preferred option? No, I do not think so. This should be the least preferred option, right? But sometimes we end up using inspection or audit. We end up doing that. There are three types of inspections. One is the source inspection. Inspection which is carried out at the source location, right? If I hire a manufacturing plant for manufacturing my shoes, sports shoes, I go there and do the inspection of the sports shoes which are manufactured. That is called as source inspection. Mistakes detected close to source can be reworked or corrected quickly before it is passed on to the end user. The second inspection technique is called as informative inspection. Inspection which is carried out to investigate the cause of any defect found so that action can be taken, right? It also provides information about defects after it has occurred, after a defect has occurred, right? And then you have judgment inspection. Inspection which is carried out to separate the good units from the bad units once processing has occurred, right? It doesn't decrease the defect rate. It just differentiates between the good ones and the bad ones, good and the bad, right? Ugly is, training you on this. All right. However, even before the inspection part, you need to look into your statistical process control whether this is possible or not. Control charts are very effective if you want to monitor your process on an ongoing basis. What is the purpose of statistical process control? The purpose is to indicate when a process is working at its intended best. Only common cause variation is present in this situation. Look at this diagram here, right? Nothing is falling outside your control limits or your specification limits. And your control limits are within your specification limits. So nothing is wrong with this. But however, even within this, you see these data points which are slightly away from your mean, right? This one might be on the mean. This is not on the mean. Slightly away from the mean. This slight variation inherently exists in the process because of common cause variation. There's something called as common cause. You cannot get rid of that. You need not take any corrective action if the data points are within your limits, right? This small variation, right, would be there in any process, no matter what you do. Unnecessary actions, if you take, may actually increase the process variability. It might be counterproductive for you all. So we need to be aware of that. A stable process is one that is consistent over time with respect to the center, that is with respect to your mean, here, the center line, and the spread of the data. This is the spread of the data, right? How far away your data points are from this line mean, that is going to speak about the spread of the data here. Control charts help you monitor the behavior of your process to determine whether it is stable or not. Stability of your process is monitored using your control charts. If all the data points are falling within your control limits, you say that the process is stable, provided your control limits are within your specification limits. Yep. What is a special cause and what is a common cause? What is a special cause in the first place? Special cause is a cause which is different, which falls outside your limits. It's a special situation. It is not business as usual. They are unusual occurrences, Normally, you do not see such occurrences in the process, and that is going to impact the stability of the process. It's going to impact the stability of the process, right? That's extremely important. An assignable cause means you can assign a special reason for that, on why a data point is falling outside your control limits or specification limits. Hence, it is called as assignable cause. You can assign some reason to that, right? It is assignable. It can be discovered and corrected at the machine level. You can take the corrective actions, right? And you most interestingly observe that there is a special cause or an assignable cause. Identification and correction of the special causes often requires intimate knowledge, understanding of the manufacturing process, right? You identify the special cause, but sometimes it might be business as usual. It might be falling outside the limits, but it might be a norm probably for you all. You might tend to see those kind of values only if you have clear understanding of the manufacturing process, or about the domain that you're working in. Then you can easily identify and take corrective actions on the special causes, right? Sometimes the special causes, just by the face value of that, might not be a special cause. What is a common cause? Anything which is within the control limits, that is your common cause or chance cause. And that variation is inherent in the process. You cannot get rid of that, right? These are uncontrollable factors, right? They occur randomly in the process, and that's all right. These causes are often referred to as background noise or chance causes by Shewat. He's the person who has come up with that. And the word assignable causes also was coined by Shewat. And common cause by Deming. Their special cause was by Deming. Assignable cause by Shewat. So just remember from the general knowledge perspective, right? So it's inherent in the process. So the causes of variation that result in ICC cricket ball circumference, that example which we have taken, when only common cause of variation are present in the production process, the process is said to be stable and in control. It is predictable. You can build prediction models on top of that. And all of its outputs will follow the same probability distribution over time. We have discussed about probability distribution earlier, so we need not look into that again. Here, by the way, cricket balls look like that for people who do not know cricket, who has not watched cricket. Now comes the most interesting part of our discussion, and that is your control charts. A control chart is a statistical tool which is used to distinguish between the variation in the process which result from the common cause and your special cause. You'll be able to distinguish that. It presents a graphical display of the process stability or instability over time. You can monitor your inputs, you can monitor your outputs, and also you can monitor the parameters. You can monitor the parameters. Are used for identifying the presence of special cause variation within the process. So in short, you can identify your special cause variation, your common cause variation in a process using control charts. Do not confuse your control limits to your specification limits. Specification limits are provided to you by the customer. Control limits are automatically calculated based on the data points. Control limits do not tell us if we meet the specification limits or not. They do not say so. They're just going to monitor your process. That's it. Because sometimes your control limits might be outside your specification limits also. Upper control limit can be here, and your lower control limit, you can have your upper specification limit and lower specification limit here. So all that is possible. Control limits neither identify what is a special cause, it's not going to tell you what is a special cause, or it's not going to remove the special cause for you. It will just help you detect the presence of the special cause variation in the process. It will just detect that there is a special cause in the process. That's it. All right, let us understand this. Here we have the control limit, upper control limit and lower control limit. The center line or the average of the mean is there, right? If your process, is 1 sigma away from the mean, then 68% of the times you're going to meet the customer requirements. You're going to meet your objectives. If your process is 2 standard deviations or 2 sigma away from your mean on either side, right? On either side, then you call that as a 2 sigma process, and 95% approximately of your results are going to meet the requirements, customer requirements, right? And if you say that your process is 3 standard deviations or 3 sigma away from the mean center line on either side, you call that your process is operating at 3 sigma. And if your process operates at 3 sigma, there would be 99.7% of the data points which are going to meet your requirements, meet the customer specifications. That is how you interpret this. All right. Now let us move on and understand what are the various control charts. First of all, you need to identify the type of data. Is the data discrete data or attribute data? And is it a continuous or a variable data that you're trying to monitor? If it is a continuous data, for example, your effort, time, cost, all this is continuous data. Heights, weights of people, and all that is continuous data. And if you have only one sample size, you have collected only one sample, then you use individual moving range. If the sample size is less than 8 to 10, right, you do X bar R chart. If the sample size is greater than 8 to 10, you use X bar S chart. Range, standard deviation. X bar is the mean here, there. Individual moving range here. On the other side, if you have the count data or classification data, which is attribute data or categorical data, or categories basically, right? Within attribute data also you have two things, count data and classification data. In count data you have defects. Can I divide the defects? Can I say, here I have 1.264 defects? How can you have 0.264 defects, right? You can have 1 defect or 2 defects or 3 defects. So that is defects all about here. And if the size is fixed, if your sample size is fixed, then you go with C chart. If the sample size is variable, you go with U chart. If the sample size is varying, you don't know. Daily calls, probably. The errors in the daily calls, those cannot be fixed, right? How many calls you get on a daily basis cannot be fixed. That is the variable sample size for you, right? You use U chart. Next thing is defectives. A product can be, or a product can contain defects and still you can end up using that. But if it is defective, you cannot use that. If I do not have button for a shirt, I can probably still wear that. But if the shirt is torn, no, you cannot do anything. So you have fixed sample size and the variable sample size. If you have a fixed sample size for defectives, you use NP chart. If you have variable sample size for defectives, you use the P chart. Now, we will look into a few case studies and try to identify what control chart should we use. And we are actually going to look into a mini tab now and try to solve those case studies. And here we go. Right, let me select the mouse pointer. Here we go. These are the various case studies which we need to discuss now. Let us look into the first case study, which is bank call center. Bank call center. A bank has a call center which wants to assess whether its automatic answering system is in control or not. All right. The total number of unanswered calls against the landed calls were recorded for 21 days. Each unanswered call is a defective. Each call which is unanswered, you're classifying that as defective, right? Comment about the process, and before that, try to analyze on which chart are you going to use here. They're clearly saying that that is a defective, right? It's defective. And here in this process, the total number of unanswered calls against the landed calls were recorded for 21 days. On each day, do you know how many calls you're going to get? How many calls you're going to receive on each day? Can you fix that number? No, it's not in your control. So the number of calls which I get can vary, and most often than not, it's going to vary from day to day, right? Hence, it's a variable sample size. It's a defective variable sample size. Hence, we end up using P chart, right? So let us open this Minitab file and try to solve this now.